Good morning, and welcome to this session, and thank you for joining me on this talk about performance and Spark. My name is Luca Canali. I'm a computing engineer and team lead at CERN. I work in the Hadoop, Spark, and database services. I'm passionate about getting the best out of the investment and value of our data and database performance platforms, and I share many of the results that I'll be talking about today on social media. You can see the links in this slide. So CERN is home to the largest and most powerful particle accelerator in the world, and is also home to large and successful scientific collaborations. Here you can see a picture of the LHC and a picture of the announcement of the discovery of the Higgs boson. CERN and high-energy physics in general are data-intensive domains, so it's natural that we are looking at big data and Spark solutions for many of our use cases. We currently have platforms to run them, and also several projects that are going on that are quite interesting. Some highlights are the projects for the accelerator logging and controls, and some projects around using Spark for high-energy physics data. There will be 2 more talks and a keynote from CERN speakers at this conference. I highly encourage you to watch them. And here are the links that you can find some information on more of the projects that we are doing. So the motivation for the work that I'm going to talk about today came for me at the beginning of the year when we were running some activities around capacity planning for our platforms. We were deciding what to buy as the next generation of hardware, and we wanted to better understand the workloads and better understand, for example, some of the data analytics workloads using Parquet that our users have, and also some specialized workloads using a data format for high-energy physics that is called Root, and the integration that we built between Spark and Root. So the topic of performance in Spark is broad, so we will not be able to cover it all. I just wanted to focus on 3 main points. The first one is about methods and therefore how to think about performance problems and troubleshooting. The second point will be about tools, how to measure performance in Spark, or at least some of the main tools. And then I want to also share with you some of the examples. So there are many challenges in doing performance work, and what is easy to do is just to collect some metrics around performance. What is complicated is to get actionable insights. This requires effort and preparation. The first thing will be how to approach the problem, and then how to gather relevant data, so knowing the relevant tools and also knowing the limitation of those tools, and also being able to know the internals of the product, so to make sense of the data that you collect, and then to make root cause analysis out of it. This is all abstract, so let's see an example. Something we see often in our industry is what I call the marketing benchmark. So that would be a graph like the one you see on the right of the slide, where you have a system A in blue and then system B in red. Then you will have some metrics, for example, a throughput metric, where higher is better. And then a claim, system B is 5 times better than system A. Okay, this is a quantitative analysis, but at the same time, I'm not very happy with it when I say it, because it doesn't really tell me why system B is better than system A, and doesn't provide a root cause analysis for it. This is a key point for me, so I want to drill down on it with a very simple example. Let's say we ask ourselves the question, which is faster between these 2 cars and a bicycle? So we can say the bicycle is 1x, the small car is 10x, and the racing car is 20x. So maybe the racing car is faster, but is it? Actually, it depends. If you're racing, yes, it is. But if we have speed limits, maybe they are the same, the racing car and the small Fiat. If cars are not allowed at all, maybe the bicycle is the option. So it all depends. Just these single measurements of time or speed or throughput typically are not enough. So benchmarks often lie to us, or at least they don't give us the big picture, but we should not throw them away altogether. I use often the benchmark TPC-EDS, for example, for investigating Spark SQL. The idea is to use benchmarks as workload generators, and then investigate with tools in Spark, with tools in OS, investigate what is happening and understand what happens, for example, if we change some parameters in our systems. So what I propose is mostly troubleshooting by understanding. The idea is to measure the workload, use all the relevant tools. Also, do not approach the system as a black box, but instrument the code where it's needed. Often, we are talking about open source solutions, so that's typically easier than, for example, with some legacy systems. Also, be aware of the blind spots. The tools sometimes lie to us, or simply we don't have the information we should have, but we should be aware of that. The next thing is to make a model of why we observe a certain type of performance, where are the bottlenecks, and then we prove it or disprove it with experiment. So in summary, we want to be data-driven and produce insights. So measurements and tools, measurements of performance data is key. It comes as a second step after having good methods about investigating the performance. So what do we want to have from our measurements? We want to be able to answer questions like, why do I measure what I measure? For example, there's a certain latency and not 10 times better. Another way to say it is that, where are my bottlenecks? Are they in CPU, I/O? Where is the system spending time in the critical path of it? So what is my system doing? And if we are talking about distributed systems like Spark, this gets even more complicated because we have many moving parts. For example, we would have drivers, we would have executors, and then they will have also components, and we will need to measure all of it and be aware that we want to measure and optimize for the whole, not for the single parts. So let's see what we can do in Spark. So Spark comes out of the box with several pieces of instrumentation and tools to measure it. We will go through most of them in the next slides. And also we can complement this type of data with data that comes from OS tools. And for clusters also we want to have tools that is working at the cluster level or tells us, for example, what is happening on the cluster manager. So the first tool that most likely you're familiar with, it's a WebView. Just point to the driver port 4040, and you will see details on jobs and stage execution of how are our jobs going on in the execution and some of the metrics, as you can see in this slide. I will just go quickly on the standard tools because I suppose that you're familiar with that. Another point, if we're moving higher in the stack, is, for example, to get execution plans. Here we can get the execution plan, for example, showing a scan from Parquet with actually some nice metrics that tell us how many rows have been read and what is the scan time. Also, a more complex plan with joins will show the joins. And also, that's a different tab. So if we are looking at the stage tabs, we can also have DAGs and see in the details of what is happening, for example, executing that particular stage. Drilling down, we can see what the tasks are doing, where they are spending time. This is the event timeline, again, in the web UI. We can see for each executor the tasks that are being executed and if the time is spent in the different parts, for example, just executing or shuffle time, et cetera, et cetera. So this is getting into the details. That's exactly what we want if we want to characterize where the time is spent. Another way to get details on the execution is by taking the Spark metrics from the REST API. This again, you can find in the documentation how to get to this document. It's basically a JSON file, and you get a lot of details that give you the runtime, the CPU time, shuffle time, etc. And also there are details in an array of accumulators that give you also the SQL metrics. This is something that you can visualize, for example, with a browser. But if you want to have a more, batch approach to analyzing it, you probably want to get a tool that allows you to aggregate and operate programmatically on this data. So what I propose here is that one can read these JSON files, for example, with a Spark SQL. Of course, the standard reader would be the Spark history server. And to activate this function is, again, from the manual, these two configuration parameters. So if we do that, if we read this JSON file, and then, for example, we print the task metrics for the event Spark listener task end, I will get later to what the listeners are, we see the metrics that are available. And again, very useful information, runtime, CPU time, I/O metrics, JVM, garbage collection, shuffle activity, etc. So we definitely want to have all these details if we want to understand what our jobs are doing. Another naming is task info, which gives us additional values. For example, the task launch time, and finish time that we can use to calculate to compute the duration of the task. And also SQL metrics are available in this view. Once we have all that, we can write SQL, or we can use a system of our choosing to aggregate these metrics and, for example, process in batch this type of data and understand what a particular workload is doing and how much time is spent, for example, in certain activities, how many rows have been read, etc. This is very useful information to drill down. For those of you who are interested to know more, so these task metrics, they come from the code, and they are just instrumentation of time and CPU time that is, for example, here are 2 snippets of code from executor.scala in the Spark core code, and you can see that there is nothing magic out of these metrics. It's just instrumentation. You take, for example, the time at the beginning, and at the end of a task, you compute the difference, and that's it. And you can see what all these metrics do, just digging a little bit into the code. It's pretty much in plain sight. So another thing that I've done, because I wanted to have a simple tool that allowed me to see these metrics for a workload, in particular when I'm running SQL statements, is that I put together a small tool called sparkMeasure that I share on GitHub. And this is an example of the most basic use of the tool. So you can use it on Spark Shell. You just attach the jar or the package, and then you initialize the tool, and you can run with stage metrics, run a measure, and then you can put any Spark SQL or any code that runs on Spark into that, and you will get the results of your code and the aggregated metrics that come out from the metric system in Spark. And this is kind of handy because it gives you immediately what is happening with the SQL in this case, or any other activity that you want to measure. This fits very well with the command line, where I shown in the previous slide, and also on notebooks. This is an example that I've run on the Databricks notebooks. It's also possible to use sparkMeasure offline, like the event log. There we can instrument pieces of code and save the metrics, or also in a, say, flight recorder mode that would save everything, and then we can read it afterwards for analysis. The granularity of the metrics that we can collect are at the stage level, which has also lower impact on the performance, or the task level, where we get the metrics for each task. The tool is written in Scala, but it works for Scala and Python command lines or notebooks. Another key piece of technology, if you want to instrument your code, is the Spark Listener. It's quite easy to use. Here I have a snippet of code that you can use if you want to experiment on it. The Spark Listener is the method that is used by Spark to send the task metrics, let's say, from the executors back to the driver, so to a program that can analyze them. This is what the WebView uses, for example, and how the event log is written. And also, sparkMeasure just hooks on the Spark Listener infrastructure. So you just need to create a class that extends Spark Listener. Then basically you will have methods that override the definition, for example, of on stage completed, and you will get all the details in your code. And you will just need to attach this additional listener to the Spark context, and you will have metrics that come to your code. It's very simple. For example, you can see sparkMeasure is just a few tens of lines of code. And this is something that you might want to do to instrument your workloads and your code. Now we get to some examples of how this plays out and how having the instrumentation can help understanding Spark workloads. We start with something very simple, that is the analysis of Parquet workload. This is an SQL that just reads a table. This is a table in Parquet from the TPC-DS benchmark. And this SQL will just read the entire table. It takes about 59 minutes to read the table. This actually runs on a cluster of 12 nodes and about 48 executors in total. And we can see the duration of the task is 1.3 minutes, and it's reading almost 200 gigabytes of data. This you can find also with the WebView UI data. Then we run an SQL that is basically the same. I just changed the where condition. This is a different column. And also in this case, I use the value of that basically has a zero result set, so we don't have to deal with many, say, rows being returned. We just want to scan the table. But this time, the system is very clever. The query runs in 3 seconds, basically does no work. This is because the filter is pushed down to Parquet, and Parquet has statistics. and can understand from knowing the minimum and maximum value of the columns that basically there is no data that can fulfill this condition. So then we have two queries that are almost the same, and they have a different amount of data that is being read, so a much different execution profile. The execution profile we find with the metrics, and then we need to understand what's the difference. So one thing that we look at is the execution plan, and understand that in the second example, the one that goes fast, we have predicate push down. And the first example, we need to dig a little bit more, and then we look at the internals and some of the, say, knowledge about the system, and we find out that in the first case, the pushdown is not available because the predicate was on a decimal data type, which is at the moment doesn't allow the predicate pushdown. So with metrics, we understand the difference on two workloads that look a little bit the same, and so it allows us to fully understand why they are different. More examples on Parquet. This is about CPU. Again, a similar query. We're just reading a table from the TPCDS. This is a different table, a little bit smaller in this case. And this case is done locally with just one task run at a time, so this local one. Because here I want to investigate really how Spark is reading and how much CPU and how much I/O is done for reading a table. What I find in my test system is that the execution runtime, which is the same in this case as stage duration, because I'm using only one task at a time, is about 8 minutes. And the CPU time is what you see there at 5 minutes, 0.4. And so it means that the CPU is about 70% of the runtime. First conclusion, reading Parquet is very much CPU intensive. The difference in time gives me the I/O time, or at least a guess of the I/O time. I also confirm that is the I/O time using OS tools. At the moment, we don't have in the instrumentation in Spark a way to tell exactly that the I/O time is a certain amount. But we could guess from the difference between runtime and CPU time, and then confirm with OS. If I have a CPU-bound profile, what I want to do typically is stack profiling and flame graphs. This is a visualization that is very popular these days for many type of platform and systems to understand where the CPU cycles are spent. My currently preferred profiler is an async profiler. The tool for flame graphs can be downloaded from Brendan Gregg's website. And what this gives us is the stacks that are being sampled at a given frequency, and then they are put all together. And so we can see from the longer, say, names that we see in the graph, we can see where most of the time is spent. And the fact that we have a full stack gives us also the context of where this time is spent. Now, the fonts are very small, but here, if you see later from the slides, you can drill down on the various pieces, and you will see that the time is spent in the Parquet vector reader most of the time. And then it's possible also to drill down on little details, understand how much time is spent, for example, in the snappy compression, and also other little things that may be useful for finer drill down. Another technique that I would like to talk to you about is how to study this workload at scale. So we start scaling up on a single box. So this is a test box with 20 cores. It's 2 CPUs of 10 cores each. And so what I've done, I've started running this Parquet workload, so reading an entire table from Parquet, and the table is cached in memory. And so I read it at an increasing number of concurrent tasks. And then I plot the speed up as defined by this formula. So this is the response time when running with only one task at a time over the response time for a given number of concurrent tasks that are noted as P. So in an ideal system, you will see that the speed up goes up linearly as we increase the load. In real life, at one point, this starts to bend down, so there are some saturation effect. And this is what I found in this test system, that at load starting, let's say, from higher than 10 concurrent tasks, this starts bending down. So how to drill down? So what is happening? There are more tools that can help us, and this actually, I find it interesting because it highlights an important point in modern systems is that the CPU to memory throughput is becoming more and more a bottleneck in workloads that are CPU bound. Because a CPU can either execute instructions or wait for memory. And when it's waiting for memory, so stalling for memory cycles, this can reduce the performance of our systems and reduce the scalability. There are ways to investigate that. One is to measure the instruction per cycle metrics. This comes from CPU hardware counters, and also there are tools that allow to do this type of measurements like perf, and more tools that I describe in that link. We don't have time to go through the details. And also it's possible to measure the throughput between CPU and memory. And in this case, at the higher load, this was getting close to the maximum throughput of the system. So the maximum throughput that was measured was 80 gigabytes, and from a benchmark, I found that that particular test box could go up to about 100 gigabytes per second. So in terms of things that I've learned from this test is that, for example, reading Parquet with that particular hardware was limited to about 3 gigabytes per second. CPU is a bottleneck. There is a high throughput between CPU and memory at a high load, and this brings also the possibility of further optimizations, for example, in the Parquet reader, but also gives us an indication of what is a typical throughput we can expect for the hardware, the piece of hardware that I was using there for the test. So it was a useful indication for me for the capacity planning and hardware acquisition that we need to do. Very quickly, I want to mention also some pitfalls on the CPU utilization. It's very important to measure CPU utilization, but it can be misleading in some cases. So I've shown the results of scaling up the workload up to 20 cores, because I had 20 cores in the machine. But what happens if I go higher? Actually, there are 40 threads. So at one point, if I increase the load, I'm using threads that they will share physical cores on the machine. So what happens? The OS will keep summing up CPU cycles. But at the end, I end up like my CPUs at one point have half the speed. So when I'm going from 20 concurrent tasks to 40 concurrent tasks, the CPU time keep going up. So but the throughput doesn't really go up. Basically, the elapsed time stays to about 20 seconds for this workload. So it's as if the CPUs have half the speed. And this can have really consequences, especially if you are running in multi-tenant systems. So maybe the extra load is generated by other users, and so you might be confused. So why my CPUs were faster yesterday and slower today? So there can be effects like this to be reckoned with. OS tools are also very useful, for example, to investigate extra CPU cycles that can be spent in the garbage collection. For this workload, for example, I figured out that if I don't allocate enough memory to read the Parquet table, then the garbage collection goes up and becomes quite important. So the execution time goes up, and I spend a lot of time that I can see in JVM garbage collection time. But even more time is spent on the CPU. If I measure with the most basic OS tools, PS, if I measure the CPU consumed by the JVM, I see that it's much more than what is reported for the executors, because there is much more CPU cycles that are consumed by the JVM. So those are big pitfall, and we need to allocate memory that is enough for the workload, and it's something to look at. So going at scale, I've shown the measurements now for a box. So first a single CPU, then I scaled it up to 20 cores, 40 cores. Let's say now we want to scale to multiple machines, which is actually the business of running distributed systems in Spark. So one typical problem here is to be able to keep the system utilizing the resources that are available. In an ideal system, we could have a workload that has 100 cores and works with the 100 cores up to a time t0, and then it stops. In a real system, there could actually be dips where the utilization goes down and goes up again. Maybe the area between red and blue are the same, but the elapsed time is different. That's because we are not utilizing the resources fully at all time. So stragglers, so slow tasks can cause this, and there are many reasons for that. Sometimes it's slow hardware, busy nodes, nodes with problems. Sometimes it's more a software problem. It could be due to skewing data and partitioning that makes it so that our task cannot execute all at the same time. And these problems are amplified by the fact that Often we have multiple stages in our jobs, and one stage has to finish before the next stage can start. And so the utilization can go down and stay down, and can be frustrating to see why don't we just continue the work. That's because there are stage barriers. So this is an example. Also, it shows an example of the analytics that I was mentioning in a few slides before. So this is taking start time and finish time of the task for a given job and plotting them using a notebook. And we can see that at the beginning, the system is going at the number of cores that are allocated for this system. And then at one point, the workload starts to finish, and so the task finish, and the amount of utilization goes down, and then I have a very long tail of stragglers that actually keep my job for a longer time. And I'm not utilizing the system for the entirety, for all the resources that I have. The data sources here were measured with sparkMeasure. Also, event log and reading JSON files will work for this. And also, of course, notebooks are a very good way to analyze this. Same graph, but now I add one more dimension. So I use color to plot basically a three-dimensional plot. So now I can see the details of the executors. I show this as an example of how you can drill down on the performance of your jobs using analytic tools, basically using the tools that Spark provides to analyze Spark in a way. And with this one, I figured out that there were 2 nodes in this particular cluster that were slow. And the lesson learned is identify and remove and repair non-performing hardware from the cluster. This will make everything run quite faster. So if you want to understand when you have problems with lower execution, lower utilization of your cluster, one way is just to refresh the web UI on the executor tab. Here, for example, I have 480 cores allocated and 480 tasks. So everything is running fine. Then during the execution of the job on the same system, I figured out that at one point the utilization goes down, so I know I will have a problem. This is just a spot measurement. Of course, it's not as nice as a full analytics, but this can be done in real time. A better way to do this in real time is to measure and plot. And this is done using Grafana as a way to plot it. And as a source, these are the drop wizard metrics that are integrated into Spark, with the source that is active tasks, which is active by default. And this measures a workload on TPC DS benchmark on 60 executors. And we can see that indeed the utilization goes down a lot in many occasions. If you want to do this type of graphs and collection of data, these are some of the pointers, so you will have to configure the Spark metrics, conf to metrics properties in a proper way so that you will have the proper sync that you need. And then the active task source is active by default in Spark. The architecture is also quite interesting in this case because the metrics are sent with the drop wizard metrics library from the executors down to the sink. So this it's quite good. While with the listeners, they would go from the list from the executors to the driver. So we don't have time to talk about all the details. I've just mentioned a few of the topics that I've been working on. Of course, there is more. There are optimization on the shuffle operation, SQL plans, better understanding of stragglers. This could be really 2 or 3 more presentations about that. Another point that I want to make is that the instrumentation that Spark has at the moment is quite useful, but still has room for improvement. There are many areas where it can be improved. Some of the areas are, in terms of macro things that need to be improved, are how to find the bottlenecks on the system. This still doesn't come out of the box. You still have to do a lot of work to fully understand where the bottlenecks are. So I've shown some of the tools that you can use to collect data and understand that. Also, it's difficult to link OS metrics and Spark metrics at the moment. For example, if I want to know how much time I'm spending reading HDFS, that could be difficult to find at the moment. And also, there is room for improvement on user-facing tools. At the moment, I'm working on investigating on how to link the Spark executor metrics, like CPU measured on the executors, and the drop wizard metrics that allow to send this information to Grafana, like in the graph that I've shown a few slides ago. So in conclusion, I want to iterate on the 3 main points of this presentation. The first one is that to do performance analysis, you need to think clearly about performance, have a good approach to it. I would say an approach like a problem in experimental science. Then you need to know your tools, experiment with them, build a tool set, experiment, use also active benchmarking to see how the tools work and what the limitations of those tools are. And the last point is that Spark performance is a field of great interest and really in development. There are many gains to be made, and if you can really tune a workload and reduce the amount of hardware that is needed, this can be a big gain also in terms of investment in the infrastructure. So measure, build tools, and share the results with the community, I would say, is the key point here. With this, I would like to thank the organizers for the invitation to speak, my colleagues for collaboration, and thank you very much for your attention.
Thanks a lot, Luca, for the wonderful bag of tools and insight into how to really look into the performance. I think we don't have enough time for questions. We'll take only one question. There's a mic at the end. If you have a question, please make it short and make it succinct. If not, then thanks a lot and welcome. Go ahead.
In your example with a machine with 20 cores, the speed up starts to saturate after 10 concurrent tasks. Why is not linear at least until 20 concurrent tasks?
Yeah, so there was saturation effect was measured, and it comes from the utilization on the memory. So at one point, starting from 10 concurrent tasks, the system is spending more and more cycles stalling from memory, for memory access. And this is shown also on the graph that shows instructions per cycle. Instructions per cycle starts to drop, meaning that the CPUs have to more and more stop and do a last level cache miss and wait for memory to come. So basically, memory in modern systems is the new disk. So it's, at one point, we saturate the channel reading from CPU to memory, and this is a big topic in new CPUs. CPU vendors are working a lot on this. As we have more and more cores and more memory, there can be a bottleneck between the two. And this is shown in the graph of speed up against the number of concurrent tasks.
Okay, give a good big hand to Luca.
Thank you.